Hello and welcome to the Deep Dive. Today, we're really digging into the world of solar energy. We've got this incredible material you shared, a really comprehensive workshop outline. It's called Solar Energy and Its Applications, a strategic pillar for sustainable energy.
That's right. And our mission for you today really is to cut through the complexity. We want to give you a solid, actionable grasp of the basics, how systems are designed, and honestly, the most exciting part, the practical ways you can actually use this stuff.
Yeah, we're going to cover it all, from, how a solar panel actually works, right down to designing and even automating your own smart solar projects. And this is where it gets really cool, I think. It's not just about huge power plants anymore.
Exactly. It's about how solar can become this smart, integrated thing in your daily life.
Okay, so to really get a handle on solar power, we need to start with the basics, right? A lot of people just think, oh, panels on a roof. But there's a key difference in the types of systems out there, isn't there?
Oh, absolutely. It's really important to get the split between photovoltaic PV and solar thermal. PV is probably what most people imagine. It uses those semiconductor cells, usually silicon, to turn sunlight directly into electricity.
Okay, so PV makes electricity.
Got it. Right. Those are the panels you see on homes, businesses, powering things directly. Solar thermal, though, is different. It uses the sun's heat. It warms up a liquid, often water.
So it's about heat, not electricity directly.
Exactly, for things like heating your home's water or your pool, or even on a massive scale in concentrated solar power plants, using that heat to make steam and drive turbines. So yeah, PV for electricity, thermal for heat. Big distinction.
Yep, makes sense.
Yeah.
So zooming out a bit, why is embracing solar, so crucial? Why is it this strategic pillar for a sustainable future? What are the big benefits?
Well, this really gets to the core of it. The sources we looked at really hammer this home. First off, it's inexhaustible. The sun isn't running out anytime soon, right? It's truly renewable.
Right, unlike fossil fuels.
Precisely. And crucially, when it's operating, it produces zero greenhouse gas emissions. So it's a direct tool in fighting climate change. Plus, it cuts down our reliance on those finite fossil fuels, which helps with energy security, and can actually stabilize energy prices long term.
Stability, that's interesting.
Yeah, and maybe one of the most powerful things is just how versatile it is. It can power huge grids, sure, but it can also bring electricity to really remote places, areas where running traditional power lines just isn't feasible.
That's a huge point, the accessibility. Okay, powerful benefits. But let's get into the nuts and bolts. For a lot of us, the how is still kind of a black box. Can we open it up? What are the essential bits and pieces of a typical solar system?
Definitely. Breaking it down makes it much less intimidating. So first up, obviously, are the solar panels themselves, the PV panels. You generally run into three main kinds.
Okay.
There's monocrystalline. These are usually black, look quite sleek. They're the most efficient, typically around 18 to 24%.
That's quite high.
It is, which means you get more power from a smaller area. But they are the most expensive. Then you've got polycrystalline, often bluish, maybe a bit marbled looking. You're a great middle ground. Efficiency's still good, maybe 16 to 20%, and they're more cost effective.
So better for bigger roofs, maybe, where space isn't the main issue.
Exactly. If you've got the space, poly can be a really smart buy. And then there's thin film. Less efficient, definitely, but super flexible and light. You can put them on curved surfaces, portable chargers, that kind of thing.
Interesting. So different tools for different jobs. And what about installing them? Is there a best way?
Yeah, generally for maximum sunlight capture, you want them facing geographic south if you're in the northern hemisphere. And the angle, roughly the same as your latitude. That's the rule of thumb.
Okay, that makes sense. So the real takeaway here isn't just chasing the highest efficiency number. It's about matching the panel type to your actual situation, your roof space, your budget.
Absolutely. It's a balancing act. Now, next up, inverters. These guys are critical, but often overlooked.
Right, they change the type of electricity.
Exactly. Panels make direct current DC. Your house runs on alternating current, AC. The inverter does that conversion. There are a few types here, too. String inverters are common, pretty economical. They connect a whole string or group of panels together.
Okay, the standard choice for a while.
Yeah. Then you have huge central inverters for, like, solar farms. But the really interesting ones now are microinverters.
You mentioned these, one for each panel. How does that work?
Yeah, one little inverter bolted to the back of every single panel. The big advantage, think about shade. With a string inverter, if one panel gets shaded by a tree or chimney,
It drags the whole string down, right? I've heard that.
it totally does. But with microinverters, only that one shaded panel's output drops. The others keep working at full tilt. It's a massive improvement, especially for roofs that aren't perfectly clear. Plus, you can monitor each panel individually.
Wow, okay. That really does change things.
Yeah.
Make solar viable for more places.
Hmm.
What about hybrid inverters?
Hybrids are super versatile. They can manage power coming from your panels, going to or from your batteries, and interact with the grid all in one box. Really useful for systems with battery storage.
Speaking of storage, batteries. What's the lowdown there?
Okay, batteries. They let you store that extra solar power you generate during the day so you can use it at night or when it's cloudy. The main comparison in the sources is between lead acid and lithium ion.
The old versus the new, kind of.
Pretty much. Lead acid is older tech, cheaper upfront, yeah. But their lifespan is shorter, maybe 3 to 7 years, and they need regular maintenance, like checking water levels.
Okay, more hands-on.
Definitely. Lithium ion, on the other hand, well, they cost more initially, but they last way longer, like 10 to 15 years. They're more efficient, lighter, and basically zero maintenance.
So lithium-ion seems like the way things are heading.
It really is becoming the standard. More bang for your buck over the long run. There's even a formula in the material for sizing them. Battery capacity equals daily consumption divided by system voltage, then divided by depth of discharge, or DOD.
Whoa, okay. Maybe don't worry too much about memorizing the math right now, but that depth of discharge thing, DOD, that sounds important. It's not just about the total size, is it?
Not at all. DOD is crucial. It's how much of the battery's total capacity you regularly use. Draining a battery completely or close to it drastically shortens its life. Understanding DOD helps you size your battery bank correctly so you're not discharging it too deeply. It makes the battery last longer.
Right, so using it smarter means it lives longer. Got it. What about charge controllers? What do they do?
Think of them as the battery's bodyguard. They sit between the solar panels and the batteries and regulate the power flow. Their main job is to prevent overcharging the battery, which can damage it, and also stop it from discharging too deeply, which also kills it.
Okay, essential for battery health. Are there different types?
Yep, two main ones. PWM, which stands for pulse width modulation. It's simpler, cheaper, kind of like a basic switch, on, off to control the charge. Fine for small, simple systems.
The basic model.
Right, but then you have MPPT, maximum power point tracking. These are much smarter. They constantly adjust the electrical load on the panels to find the sweet spot, the point where the panels are producing the absolute maximum power possible under the current conditions, sunlight intensity, temperature, etc.
So it squeezes out more power.
Exactly. It can convert excess voltage from the panels into extra charging current for the battery. This can boost your energy harvest by up to 30% compared to PWM, especially in colder weather or when the battery is low. So for bigger systems, MPPT is usually worth the extra cost.
30%. Okay, that's significant. Makes sense for serious setups. And finally, what about protection devices? Safety's got to be key.
Absolutely paramount. You need several things. DC breakers, like circuit breakers in your house, but for the DC side. Solar fuses to protect panels, especially if you have multiple strings. Surge protectors are vital, especially against lightning.
Yeah, don't want lightning frying your system.
Definitely not. Then proper earthing systems or grounding. And the sources even mention things like heat and smoke sensors for the areas where your inverter or batteries are housed. It's all about ensuring safety and making sure your investment lasts.
That's a really thorough look at all the pieces. Okay, so now we understand the components, but knowing the parts is one thing. How do you actually put them together? How do you design a system that works for your needs? What goes into that planning?
Right. Designing isn't just throwing panels on the roof. It's quite precise. The sources highlight a few key things you absolutely need to figure out first. Number one, your daily energy consumption in kilowatt hours.
How much power you actually use.
Exactly. You need to audit your appliances. How much do they consume? How long do they run each day? That's your target. Then you need to know the peak sun hours for your specific location.
That's not just how long the sun is up, is it?
No, it's different. It's the average number of hours per day when the solar irradiance, the sunlight intensity, reaches 1,000 watts per square meter. It's like the equivalent hours of perfect sunlight. This number varies hugely depending on where you live and the time of year.
Okay, so if I live somewhere cloudy like Seattle, my peak sun hours are lower than, say, Phoenix.
Much lower, yeah. And that directly tells you how many panels you'll need to meet your energy target. Lower sun hours mean you need more panel area. You also need to consider the type of loads.
Meaning?
While things that run constantly, like your refrigerator or freezer, need consistent power and therefore impact your battery sizing more than things you only use occasionally, like a TV or a blender. Continuous versus intermittent.
Got it. And are there tools to help with this? It sounds complex.
Oh, yeah. Professionals use sophisticated software. The sources mention things like PVSOL or PVSYST for really detailed simulations of system performance. There's Homer Pro, which is great for optimizing hybrid systems, maybe solar plus wind, plus batteries, plus a generator. And tools like SketchUp combined with Helioscope let you build a 3D model of your house and roof to analyze shading from trees or other buildings very accurately.
Wow, okay. So the pros has some serious tools to get it right. Now, this next part I find really exciting. How does solar go beyond just generating power and become, well, smart? The workshop talks about automation, programming.
Yeah, this is where technology really enhances solar. How can we make these systems more efficient, easier to manage, even interactive? The materials highlight a few cool platforms. First, Arduino.
Arduino, I've heard of that. The little circuit boards, right?
Exactly. They're super cheap, open source microcontrollers, like tiny little programmable brains. Perfect for learning and for simple control tasks in a solar project. You could use an Arduino with some sensors to, say, monitor your battery voltage and turn off non-essential loads if it gets too low.
Okay, basic automation.
Right. Or maybe trigger a cooling fan for your inverter if it gets too hot. Then, stepping up in power, you have Raspberry Pi.
A mini computer.
Yeah, it runs Linux. It's much more powerful. Ideal for collecting data from lots of sensors, doing more complex processing, connecting to the internet. You could use a Pi to log all your system data panel output, battery charge, energy usage, and then send it up to the cloud.
For remote tracking.
Precisely.
Yeah.
And for visualizing that data, there's Node-RD. This is a really cool visual programming tool. You basically drag and drop nodes and connect them to create data flows. It makes it easy to build web-based dashboards.
Dashboards. Like a web page showing my solar stats in real time.
Exactly. Battery level, how much power the panels are making, what you're
Yeah.
consuming, all displayed graphically in your browser. Makes it really easy to understand what's going on.
That sounds incredibly useful.
Yeah.
And what about controlling things remotely or getting alerts?
That's where MQTT and Blink come in. MQTT is a super lightweight messaging protocol. Think of it like super efficient texting for devices. Perfect for sending small bits of data, like sensor readings from your Raspberry Pi, reliably over the internet to a server without using much bandwidth.
Okay, efficient data transfer.
And Blink is a platform, mainly a mobile app, that lets you easily create custom interfaces on your phone to monitor and control your connected devices.
Control them so I could like turn something on or off from my phone.
Totally. Or, more relevant here, you could get alerts. Set it up so Blink sends a notification to your phone if, say, your battery voltage drops critically low, or maybe if your inverter compartment gets too hot. It gives you that remote oversight and peace of mind.
Wow. Okay. That combination, Raspberry Pi collecting data, MQTT sending it, Blink showing it and letting me control things, that makes a solar system truly smart and interactive.
It really does. It moves beyond passive generation into active, intelligent energy management.
Okay, this is brilliant. We've gone from components to design to smart controls. Now let's make it even more real. The source material actually walks through setting up a small system, getting hands-on.
Yeah, this part is great for making it tangible. It outlines how to build a small, basic, 100-watt, 12-volt system. Perfect starter project. It lists exactly what you need. 100W, 12V solar panel, a simple 10-amp charge controller, could be PWM or MPPT for this size, a 12-volt deep cycle battery, maybe 50 amp hours or more.
Deep cycle, that's important for batteries that get discharged often.
Right. Crucial. Not a car starting battery. And optionally, a small inverter, say 300 watts if you want to run AC devices. And make sure it's a pure sine wave inverter if you're running anything sensitive like electronics.
Right, pure sine wave for clean power. What else?
You'll need the right solar wiring, often with standard MC4 connectors which make connections safe and easy. DC breakers, fuses for protection, and basic tools like wire strippers and a screwdriver.
Okay, standard kit
Hmm?
and the connection process. You mentioned a specific order earlier.
Yes, absolutely critical for safety and for the charge controller to work properly. Always connect the battery to the charge controller first.
Battery to controller first. Got it. Why?
So the controller can read the battery voltage and set itself up for the correct system voltage, 12V in this case. Then connect the solar panel to the controller's input terminals. Make sure you get the polarity right, positive to positive, negative to negative.
Okay, battery, then panel, then the load.
Exactly. If you have a DC load, like a 12V LED light, connect it to the load terminals on the charge controller. If you want to use AC appliances, connect the inverter directly to the battery terminals with a fuse on the positive wire close to the battery, and then plug your AC device into the inverter.
Fuse the inverter connection, right? Safety first.
Always. And put DC breakers between the controller and battery, and maybe a fuse between the panel and controller too. Then you can do basic checks, like using a multimeter to check the panel's voltage in the sun, or just watch the LEDs on the charge controller to see if it's charging. It's a really rewarding little project.
That sounds totally doable, a great way to learn. But the material doesn't stop there, does it? It gives us 3 specific small project ideas that combine solar with that smart tech we talked about.
Yes. These are fantastic examples that really show the potential.
Solar-powered lighting with a motion sensor. This is classic off-grid smart lighting.
Like for a shed or pathway.
Exactly. Use a small panel, maybe 10 watts, a 12-volt battery, a charge controller, an Arduino, a PIR motion sensor.
PIR, that's the one that detects body heat.
That's the one. Plus a 12-volt LED light and a relay module. A relay is just an electrically controlled switch. The Arduino uses a tiny bit of power to flip the relay, which can then switch the higher power needed for the LED light on or off.
Ah, so the Arduino is the brain.
Right. The Arduino code is simple. Read the PIR sensor. If it detects motion, tell the relay to turn the LED on. Wait a bit, say 30 seconds. If there's no more motion, tell the relay to turn the LED off to save power. Smart solar-powered security light.
Brilliant. Okay, project 2.
Project 2. Remote monitoring of a solar system. This builds on having a basic solar setup. You add a Raspberry Pi, some sensors, specifically voltage and current sensors, like the little INA219 module is popular for this, and connect the Pi to your Wi-Fi.
Okay, adding brains and connectivity.
Yep. The Pi reads the voltage and current from the sensor connected to your battery. It then uses the Blink library software that makes talking to Blink easy to send that data over the internet to the Blink servers.
And
then you open the Blink app on your phone, and boom, you see real-time graphs and numbers showing your battery voltage, how much current is flowing in or out. You can check your system's health from anywhere with an internet connection.
that's amazing. Real-time data in your pocket. Project 3.
Project 3, smart solar-powered irrigation system. This one is really cool for gardeners or small-scale farming. You need a slightly bigger panel, maybe, say 20 watts, a battery, charge controller, an Arduino again, a soil moisture sensor.
Stick that in the dirt.
Yep, you stick the probes into the soil near your plants. Then you need a small 12-volt water pump and another relay to control it.
Okay, so the Arduino reads the soil moisture.
Right. Periodically, it checks the sensor reading. If the soil moisture drops below a certain level that you've set in the code, meaning the plants are getting dry, the Arduino tells the relay to switch on.
And the pump starts watering.
Exactly. The
Yeah.
pump runs, watering the plants. The Arduino keeps checking the moisture sensor. Once the soil moisture reaches the desired level, the Arduino tells the relay to switch off, stopping the pump.
Wow. That's fully automated, solar-powered, water-saving irrigation.
It really is. Smart resource management in action, powered by the sun. These projects just show how you can combine these affordable technologies, solar, Arduino, Raspberry Pi, sensors, to solve real problems and add convenience.
They really do bring it all together.
Yeah.
It makes the whole concept of sustainable tech feel very practical and accessible. So we've covered a lot of ground today. We started with the fundamental physics, how solar panels work, the difference between PV and thermal. We dissected the key components panels, inverters, batteries, controllers. We looked at system design principles.
Right, figuring out your energy needs, peak sun hours.
And then jumped into the really exciting stuff, making solar smart with Arduino, Raspberry Pi, Node-RED, Blink.
Building those intelligent, connected systems.
And finally, those practical projects, actually building a small system or creating smart lighting or irrigation.
Yeah, and what